Hi, this is Charles Maggio. Welcome back to R for Epidemiology. In this screencast, we're actually going to start doing some statistics with R, which is all very exciting. So, at this point, you should have a good idea of working within R, what R objects are, what R data frames are, and how to work with them. And of course, the reason to work in R is not necessarily to learn about R programming, but to actually use R. R is a very important tool in statistics. So we'll jump right in. We'll create a data frame, and I'm creating a data frame that's going to consist of three variables. A variable called outcome1, which is drawn from a random normal distribution centered around a mean of 20 with a standard deviation of 5. A variable called outcome2, which will be Poisson distributed. Another sample of 1,000 with a lambda of 5. And a variable called group, which is going to be a factor variable, which is going to be a sample of A, B, C, and another 1,000 for each one. And we'll just run that, create this data frame, which we're going to call mydat, and we have this data frame called mydat. As we normally will, we'll take a quick look at it first using the structure function, and we see it's a data frame of 1,000 observations and 3 variables, outcome1, outcome2, and group variable. We could use the head function if we wanted to take a quick look at it. There's no need at this point. We've seen the summary function before for different objects. When you apply the summary function to a numeric object, you get a very specific result. And we're going to see this again and again. I'm going to really talk about it a little bit more. But here we're applying the summary function to the variable called outcome1 in the data frame mydat. And let's see the results that we get. And we get here a 6-number summary, which consists of the median, the mean, which thankfully so, are about 20, which is what we basically programmed in. The minimum value is 5. The maximum value is 35. There is a similar function to summary called 5num. You can return that to get essentially the same numbers, but more of a sort of minimalist approach, a little bit more brevity in this right here. There is another statistical function called the stem function, which returns the Tukey stem plot. You can't really see it as well here. I'm going to just expand this a little bit to just see what this is. This is that nice little sort of like, so here is like the first digit, and the nice thing about the stem plot is that it gives you an idea of the normality of the distribution. This is applied to the to outcome 1. Again, we could apply to outcome 2 if we wanted to and see what it looks like. And because it is a large one, you see, you kind of get a little bit of the sense of the Poisson-ness of it, perhaps, but not so much because there's 1,000 samples. It's really relatively large. But here you go. It is pretty rare, though, right? Here it goes. It really goes right out there. Another function that you will probably want to use in your initial evaluation of a numeric variable is the box plot function, and I find that to be really just a very helpful and very informative function. You should really turn to it relatively soon, and early in your evaluation of a numeric set of data. So here, just to illustrate it, if you apply the box plot function to the entire data frame, R may not be entirely sure, might not know exactly what you want, so it'll apply it to everything. I'm just going to bring it over from my other screen here. So here is the box plot result right here, and you see that it just took each variable and returned a box plot for each variable, which may or may not be what we want. Now in this case, we were probably interested in comparing the variables by this group variable that we created here, right? This factor variable. And what we can do is, instead of just specifying the entire data frame, which doesn't make any sense, specify a formula. This formula notation with the tilde we've seen in XTabs, and we're going to see it in regression analysis. We'll see it again and again, and it really just repeats over and over. And basically, you have a formula, and then you specify the data, and there may be some options afterwards. Box plot will accept a formula. What we're saying is, please give us a box plot of the variable outcome1 by group is the explanatory variable, and specifying the data from which these variables are chosen. If we submit that, what we get is, now this is pretty much what we're interested in. There are 3 groups, right? And as we would expect from a randomly drawn variable, they're not really very different. This whole data frame is really just to illustrate the mechanics of using some of these functions. There are any number of functions. There are hundreds of statistical functions in R, and here are a couple of more useful ones. I find the QQ normal function to be useful if you're evaluating the normality assumption of variables. It is essentially just a normal probability plot where you array the data themselves along one axis, along the y-axis, and array their standard normal deviates along the other axis. And if it's normally distributed, you should get a straight line. In case you need to be reminded what a straight line looks like, there is the QQ line function, which will overlay a line on your normal probability plot. And let's just see what that looks like. And in fact, it looks like a line, which is what we'd expect. One small but important factor about a variable, like about a function like QQ line. QQ line is intended for an existing plot. It overlays a line on an existing plot. It's considered a lower level plotting. And I'm just going to copy this here. And rather than specify outcome variable 1, let's see if we just apply this to outcome variable 2. Now recall, I have not asked for QQ normal on outcome variable 2. I'm just asking for the QQ line. And R will say, oh, it actually returns it. That surprises me a little bit. And now let me do this right here. Maybe, because the plot actually exists. Let's do this. I'm going to close this down. And I'm going to ask for QQ line on outcome variable 2. And I do get the error because there is no existing plot. But that's actually kind of interesting. As long as the plot exists, as long as I call a plot, QQ line will return something, whether QQ normal has been called or not. But in any event, moving right along, we are often in the situation where we want to compare numeric variables, and one of the most basic comparison tests is the t-test. And the call for a t-test in R is really quite straightforward. You use the t-test function, you specify the first numeric variable, comma, specify the second numeric variable. And if you were to do that, you get your t-test. And here we could take a quick look at the results. It specifies that it's a Welch's two-sample t-test. The two-sample part is, of course, the important part. Nothing against Welch himself, but usually eponymy is more confusing than anything else, and we'll see that when we refer to the Wilcox test. But in any event, specifies the data, specifies the t-statistic, the degrees of freedom, and the p-value. So clearly this is a very small p-value, so whatever is going on is important. Essentially what we're doing is we're saying, okay, there is a mean. The mean of the first variable, which is normally distributed around a mean of 20, which we created, is 20, and the mean of the second variable is 5, and this difference is statistically significant, very highly statistical, very unlikely this is due to chance, and it actually returns a 95% confidence interval around the difference between those two means. Speaking of eponymy, if you're interested in a non-parametric approach to comparing two numeric variables, and by the way, there's a paired version of the t-test, and you just have to put paired equal trees for a paired t-test. But we will illustrate that a little bit more here with this question of the Wilcox test. If you're interested in a non-parametric approach, there is the Wilcox test, and Wilcox refers to the American statistician, I think it's Frank, perhaps, but Wilcoxon, who wrote a very important paper in the 1940s proposing this non-parametric approach to continuous data sources. Here's the confusing part. I know when I learned the non-parametric test for comparing two independent samples, it was presented to me as the Mann-Whitney U-test, and I'm sure in some circles it still is. But in the R world, it is the Wilcox test, which I find a little confusing. But in any event, let's say we were to submit the Wilcox test, we would get a somewhat briefer test, still statistically significant. It doesn't give us all this interesting stuff, but there may be a way to get that if you really want to, and I'll show you, and we'll look at that, how to get more information from these tests in a moment. But the actual Wilcoxon test that I was taught is not for two independent samples. The Mann-Whitney test I was taught was for two independent samples. The Wilcoxon test is for essentially like paired samples. They're related, they're not independent, perhaps before or after, but some sort of paired data. And if we were to specify paired equals true, we would get the Wilcoxon test that some of us were taught as sort of like the default version of the Wilcoxon test, and we'll return that now. And we get basically the same thing for these data, whether they're paired or not. It's going to return the same p-value. That, in any event, is a quick overview of some statistical tests in R. We've looked at the 5-number summaries, some box plots, some assessments of normality, a quick t-test, how to do that, a non-parametric approach to test. Most folks will really move very quickly to things like logistic or linear regression modeling. Linear modeling or any kind of regression modeling, basic regression modeling in R, is relatively straightforward itself. And here we're going to do the same thing. It's the formula approach here. You have outcome 1 as a function of outcome 2, specify the data, and we use linear model as the function, LM. If we were to do that, we get a result. Now, one thing I want to point out about this result here is it's really quite brief, is it not? All you get is the coefficients. You don't get very much else. That's the way R works. R is sort of like a tip of the iceberg approach. It's very, very much a non-verbose approach to returning results. You have to ask for them. And the way you ask for them is you save your results to an object. What I'm doing here is I'm running the exact same linear regression model, but now I'm using the assignment operator to assign the results of this model to an object I'm calling my reg. I don't get any results there, but now I have this object called my reg, and it is actually of the class LM. It is a regression object. We said very early on that the class of an object tells R how it should behave when given when submitted as an argument to certain generic functions. So, if we were to ask for a summary of mine, now recall up here I asked for a summary of a numeric variable and I got 5 numbers. If, though, I use the exact same function, summary, but now my argument is an LM object, an object of the class LM, what I get back is a bit more information about that linear regression model object. Now I get some residuals, some coefficients with their standard errors and t-values, whether they're statistically significant or not. Of course, in this case, it's not statistically significant. This is just made-up data here. They shouldn't be. I get R squared and standard errors, F statistics, all the good stuff we're taught about in regression. If I were, for example, to ask for a plot of my reg. Now here I'm just asking for a plot, and I'm not specifying any variable by any other variable, just a plot of a regression object. I get something quite special. And first I get prompted, hit return to see the next plot. So I'm just going to return through, and here is the first plot. I'm going to bring it over here, and here is a plot. Basically it is a plot of residual values versus fitted values. Here's the fitted on the x-axis, and the residuals, you want to see no pattern, and this is sort of our usual residual plot. I'm just going to go through some of these, and if I hit enter again, now I get a normal probability plot for residuals versus standardized values. I get this is a bit more involved. This is a square root of the standardized residuals. You see the little square root thing versus the fitted values. Here is a leverage plot of Cook's distance values. But in any event, and without going into detail of what all this stuff means, this is what you're going to do when you're doing regression analysis, and you should learn that in your regression class. But in terms of R, what this means is that when you use a generic function like plot on a very special object like a regression class object, you will get very special results. In any event, that's a quick introduction to doing statistical analysis, using some basic generic statistical functions in R.